In number theory, the prime factors of a positive integer are the prime numbers that divide that integer exactly. The prime factorization of a positive integer is a list of the integer's prime factors, together with their multiplicities. The process of determining these factors is called integer factorization. The fundamental theorem of arithmetic says that every positive integer has a single unique prime factorization. To shorten prime factorizations, factors are often expressed in powers. For example, in which the factors 2, 3 and 5 have multiplicities of 3, 2 and 1, respectively. For a prime factor p of n, the multiplicity of p is the largest exponent for which par divides n exactly. For a positive integer n, the number of prime factors of n and the sum of the prime factors of n are examples of arithmetic functions of n that are additive but not completely additive. Perfect squares, perfect square numbers can be recognized by the fact that all of their prime factors have even multiplicities. For example, the number 144 has the prime factors. These can be rearranged to make the pattern more visible. Because every prime factor appears an even number of times, the original number can be expressed as the square of some smaller number. In the same way, perfect cube numbers will have prime factors whose multiplicities are multiples of 3, and so on. Coprime integers, positive integers with no prime factors in common, are said to be coprime. Two integers a and b can also be defined as coprime if their greatest common divisor GCD, a equals a1. Euclid's algorithm can be used to determine whether two integers are coprime without knowing their prime factors. The algorithm runs in a time that is polynomial in the number of digits involved. The integer 1 is coprime to every positive integer, including itself. This is because it has no prime factors. It is the empty product. This implies that GCD, 1, a equals a1 for any bar per mil beta 1. Cryptographic applications, determining the prime factors of a number is an example of a problem frequently used to ensure cryptographic security in encryption systems. This problem is believed to require super-polynomial time in the number of digits It is relatively easy to construct a problem that would take longer than the known age of the universe to solve on current computers using current algorithms. Omega functions, the function I per mil, n, represents the number of distinct prime factors of n, while the function I copyright, n, represents the total number of prime factors of n. If, then. For example, 24 equals 23, 31, so I per mil, 24, equals 2 and I copyright, 24, equals 3 plus 1 equals 4. I per mil, n, for n equals 1, 2, 3. Is 0, 1, 1, 1, 1, 2, 1, 1, 1, I copyright, n, for n equals 1, 2, 3. Is 0, 1, 1, 2, 1, 2, 1, 3, 2, see also, composite number, divisor, table of prime factors, sieve of Eratosthenes, Adesa Eurocac theorem, I copyright, n, I per mil, n, I 1/2 p, n, a Euro prime power decomposition, references. External links, prime factor calculator at the database of number correlations, a JavaScript prime factor calculator. Can handle numbers up to about 9a, 1015, fast prime factorization calculator in JavaScript. Can handle numbers up to 1020, JavaPlet, factorization using the elliptic curve method, finding factors with 20 plus digits, millions of factors and prime factors on HTML pages. List of prime factors for numbers from 2 to 5 million and growing. Prime factorization calculator. Can handle numbers up to about 9a, 1015, prime factorization a new approach.